All right, hello. I'm Laura Rogers, and welcome to the first of our Rocky Small Bodies and, in brackets, Exo Moons session. So today we first have Mario Juric speaking on initial Rubin solar system results, the performances and the first discoveries, and the expectations for early operations. All right, take it away.
Thank you. Let me check if you can hear me. Yes, perfect. All right. Thank you very much. As Laura said, I'm Mario Juric. I'm at the University of Washington, and I lead the Solar System Science Unit on Rubin Observatory. So what is Rubin? The Varese Rubin Observatory is a new special purpose observatory being built, being just completed in Chilean Andes. The idea is we build an 8-meter class telescope. We outfit it with a very large camera, 3.2 gigapixel camera, and then we start surveying the sky and basically download the sky repeatedly over a 10-year period, creating what will be known as the legacy survey of space and time. So this is what a typical night looks like when the telescope starts observing. The way to think about LSST is we're going to have roughly 500 unique pointings per night, 2 visits to each pointing, 10 square degrees per pointing down to our band of 24th, 6 bands, UGR, ZY, 4,000 unique square degrees surveyed per night, and we repeat that for 3,300 nights, or about 10 years. So when you build a telescope of this scale, you're essentially downloading the sky. And that allows you to do very different types of science from the same data set, anywhere from probing the dark matter and dark energy, mapping the Milky Way, exploring the transient optical sky, and what we're really interested in, doing the inventory of the solar system and specifically small bodies of the solar system. So kind of to lead with the punchline, here's roughly what we expect to find with Rubin over its 10-year lifetime. So right now, there are about 1.5 million main belt asteroids known. That's going to go up to about 5 million, so about a factor of 3. NEOs are going to go up by a factor of few. TNOs are going to go up almost by a factor of 10, and so on and so on. So over the next few years, expect a dramatic increase in just the sheer amount of data available on small bodies of the solar system, but as we'll see in a moment, also in the quality of it. Rubin right now is in commissioning. We started commissioning. Here's the big camera. I'm not kidding when I say it's big. It's the size of a small regional jet engine. We've started commissioning actually last year, not with that big camera, but with a smaller version. It's the size of this central, what we call a raft in the top camera picture. So with that, we observed these 7 fields, these yellow dots that you see here superimposed on what's going to be the LSST footprint when we start. And the one that we're really particularly interested in here is this one because it's fairly close to the ecliptic. So that's the sky coverage for that pointing. That Rubin SV387 field had on order of about 150 observations, 158 observations, and that allowed us to find the first asteroids with Rubin. So here are the examples. These 2 were already known, but were reimaged with Rubin. And we've submitted the unknown ones from this program, just 93 reported discoveries, 2,200 observations to the MPC about a couple of months ago. Now, the sheer numbers here are not yet impressive, but what is the precision with which of the data that were taken. So here are some first results and just quantification of how well Rubin is doing. With commissioning camera data, our astrometric repeatability is already at roughly 10 milliarc seconds level. So that's what this plot shows here. The plot on the left, the other left, also known as right, shows you that we've actually, in the time since this plot was made, we've gotten a lot better. So we have brought this down from about 10 milliarc seconds to an order of 2 or 3. So think about systematics in this telescope will allow you to start probing dynamical effects in the solar system that are on that order. On the physical properties side, This is photometric repeatability. This is photometric repeatability of stars, and I'll show you in a second that asteroids roughly follow the same curves. It's between 5 to 10 millimag for UGR for all of the LSST bands, and these plots here include both any systematics introduced by the analysis software, by the telescope, and the photon noise. When you remove the photon noise, intrinsic repeatability is at a level of about 5 millimags for U and down to 1 to 3 millimags for GRI, Z, and Y. So we're going to be able to really pin down what the magnitudes and colors of these objects are. Image quality is also pretty good with commissioning camera. We're getting roughly around 1 to 1.1 arc seconds seeing. That is expected to go down to about 0.7, 0.8 by the time the telescope is fully tuned. So stay tuned. And what I want to say here is that all these data are already available. This is what's called a data preview 1. If you're at a US institution or one of the international partners, you can go and access it at the Rubin Science platform, and everybody else, astronomy and photometry, has been submitted to the MPC. You can grab it from there. And there's a paper getting prepared. It's already at this link, RTN 095. You can go and read the draft there describing everything I just said. Now, beyond that, we've started commissioning with the big camera. And the first photon with the large camera was taken on April 15th, but the real event when we've actually shown some of those first results was on June 23rd. And I'm just going to show you the movie because it looks great, even though it's going to take 1 minute away from my talk. So here's an asteroid. We've taken about a couple hundred observations for this first look event. These are all new discoveries from Rubin. So there's 9, there's 36. But in total, in a first night, we found about 1,000, second, 1,300, then it just kept going, and these are actual observations. So these are not just randomly plotted dots. So you can see some moving fast, those are the NEOs. You can see some moving slowly, those are the TNOs. And when you unpack that, when you add the third dimension, because we have enough data to compute the orbits, this is where all the objects are. So that, I hope, gives you some flavor of what's coming. This is at the MPC as well. 2,000 reported observations, 300,000 reported observations, 2,000 discoveries. They're all roughly in this 24 square degree field around Virgo. There are members of virtually every class in the solar system. I'm just going to quickly go through this and let you read this from the data release website. Large numbers of observations. Photometry is really good. You can see there are some outliers over here. And then Sarah Greenstreet, our conference organizer, took a look at those outliers and realized they're actually spinning, and they can their light curves can be, or their rotation curves can be extracted. Here's an example of one. And this gives you a sense for photometric repeatability, just how accurate it is. And the really neat thing to me is that. So this is a 23rd magnitude object, and the light curve looks like that. So these data are available. We're not quite yet ready to serve it on the Rubin Science platform, but the community has come together and they put up this website where it's served in a nice way that can be accessed by everyone. You can scan this QR code or just download my presentation and take a look. So in the last minute or so, what's next? The science validation survey is the next thing we've been doing. We've just finished it a couple of days ago. And that is a fairly large survey that took images of roughly a third of the ecliptic. You'll see it in the next slide. And then before the end of this year, we'll start the LSST, the actual large survey. So here's the science validation survey. It's a band plus or minus 10 degrees around the ecliptic. You get a sense for how much observations we have. We expect a couple of 100,000 asteroids, new discoveries, and known objects to be found there. And just to show you that that's not just an empty promise, here's here are some of the candidates we already have on disk. And this is one of the things that we want to get to the NPC sooner than later. Another thing that we caught by accident in that survey are Atlas 3i images. Hear more from Colleen Chandler tomorrow. And next, we'll be starting the LSST. Here's a typical night with LSST. And this is what the first year is going to look like. So I think this is a good time as this movie is running. Basically, in the first year, we are going to get to roughly doubling the number of objects. Thank you for your attention, and I'm happy to take some questions.
All right, that was a great talk. Yeah, questions for anyone? And please may our next speaker come down as well. There's one up in the back.
Shubham Kanodia, Carnegie Science. This is extremely exciting. My question is, what do you think is the potential for LSST to constrain Planet 9, either directly by detecting it, ruling it out, or by constraining the orbits of the Kuiper belt objects and then refining the models that currently predict its presence?
I'm going to make a bold statement so someone can explicitly tell me I was wrong 4 years from now. But my bold statement is that we'll know either way within about 3 to 5 years. If it's there, we'll either see it directly, or we will strengthen this evidence that the orbits all align, et cetera, beyond reasonable doubt, or it'll just go away. But I think either way, we'll know if it's there or not.
Any more questions? We've got time for another one. Yeah.
So probably a very basic question, but so you pointed at Virgo, which is basically an ecliptic. But if you look at the directions, so I would have thought they'd all be pretty much moving in the same direction, but they're moving in all directions through that field. What's the explanation to that?
Most of them are moving in the same direction, but it's a viewing angle combination of their distance and how the Earth is moving at that time.
Okay.
So that's some of the NEOs are moving slightly differently. Some of them are just starting to go retrograde, and that's kind of what you're seeing.
Thank you.
Yeah, we had some fun kind of trying to figure out why is that dot moving this way. It's almost in quadrature, like that field where it was when we were taking the pictures of it.
Awesome. I'm really sorry that we're going to have to move on, but please post your question in the Slack or speak to the speaker at the end. So let's thank our speaker again.